So before we started, I really wanna refresh this HTML slide so that it just can show you guys how dedicated this HTML the AI builds. So today I wanna share a board that recently I've used in my project field link. It's called the ESP32, and as you can see, in back there it's also have the S3, this board, which is I think is really different version of ESP32, and this video is just kind of an introduction and a process or a trip that I trans from the Arduino to ESP32-S3. So I've used two development boards, and one of them is an Arduino. More specifically is the Arduino Uno R3, the kind of board many people first use when they start learning electronics. And the first time I get to know this is the 2025 summer outreach from U of T. They let us to program on this board to build a tracing car or robotic tracing car. So, but in the future or in the project I'm going to do, I found out that whether the performance or the external things is not gonna enough in my project. So I switched into the other one board is ESP32-S3, a dual USB-C development board. At the first glance, they seem to belong to the same category. Both can run code, both can connect to sensors, both can control external components. But an interesting part is this. Although both of them are called development boards, they make you think in very different ways. An Arduino asks, how do I control a circuit? But an ESP32-S3 asks, how do I organize computation, communication, storage, interfaces, power, and debugging into a complete embedded device? That is the main idea of this video. This is not just a comparison of specifications. It is not simply about saying that one board is better than the other. It is about two different models of embedded development. One is centered around control, the other is centered around systems. So, starting with the control. So, imagine a program that reads a button. If the button is pressed, an LED turns on. This can be reduced to a very simple chain: input, processing, output. This is almost the perfect mental model for understanding Arduino. Arduino makes electronics feel visible. You can see how a line of code changes the voltage on a pin. That pin can light up an LED, drive a buzzer, move to a servo, or control a motor. Never mind. So the real value of Arduino is not that it has the strongest performance. Its value is that it makes control transparent. You know where the signal comes from, you know where it goes, you know how the program connects to the physical world through GPIO, the general purpose input-output. But as projects become more complex, this simple line starts to branch. At first, it is one output and one input. Then it becomes multiple sensors and multiple actuators. Then you may want the device to connect to Wi-Fi. You may want it to communicate with a phone over Bluetooth. You may want it to store data. You may want it to drive a display, blah blah blah. Eventually, you may want it to handle networking, display updates, sensor readings, and debugging information at the same time. At that point, the original line is no longer enough. The project is no longer just input, processing, and output. It becomes the networking of interacting subsystems. And that is the real reason why moving from Arduino to ESP32-S3 matters. You are not only upgrading a board, you are upgrading the structure of the project itself. Okay, so a board like Arduino is built around a microcontroller. Its word is relatively clear: GPIO, general purpose input and output, ADC, PWM, UART, blah blah blah. So these features are all point towards one central question: how do I control external circuits? The ESP32-S3 is different. It is not just a simple microcontroller in the traditional sense. It is the SoC, a system on the chip. And in that phrase, the important word is not the chip. The important word is system. Inside the 32S3, there is not only a CPU, there is Wi-Fi, Bluetooth Low Energy, RF security, USB OTG, USB serial or JTAG, DMA, cache, external memory control, LCD interface, camera interface, security hardware, low power coprocessors, and a flexible peripheral system that can route many internal functions to different GPIO pins. On Arduino, a typical program is built around a main loop. Read an input, check a condition, control an output. This model is really very clear, and that is why it is so good for learning. But on the ESP32-S3, a project may involve network connection, Bluetooth communication, USB debugging, sensor sampling, screen refresh, system state management, file storage, and sometimes even image, audio, or lightweight edge AI processing. Yeah, AI processing. So the question is no longer just, should this pin be high or low? The question becomes, how do multiple parts of the system network together? Arduino teaches us how to build or how to control a circuit. ESP32-S3 starts teaching us how to design a device system. So the first time I see this board or I searched this board on internet, I thought it's just a simply ESP32 board, but that is not completely wrong, but it is too broad because ESP32 is not a single chip, it is a family. Classic ESP32 brought Wi-Fi and Bluetooth into low-cost embedded development, made it much easier for a small device to connect to the network. ESP32-S2 added USB OTG, focused on Wi-Fi and USB, did not include Bluetooth. ESP32-C3, single-core RISC-V 5 version, Wi-Fi and BLE is the Bluetooth low energy, focused on low lightweight, low cost, lower power wireless nodes. ESP32-S3 sits in a very interesting position. Not the lowest cost route, not just the simplest wireless node, more focused on interaction, native USB display, image input, voice, and AIoT style applications. Dual-core LT7 at 240 Hertz, or MG is giga, is I forgot, never mind. Wi-Fi, Bluetooth 5, USB OTG, USB serial, or JTAG, LCD camera, GDMA, FPU, SIMD, lots of things. So the real question is not, is the ESP32-S3 just a little faster? The better question is, what direction does the ESP32-S3 represent inside the ESP32 family? The classic ESP32 solved the problem of connecting devices to the network. The ESP32-S3 goes further and asks, how can a connected device handle more complex interaction, local processing, and debugging? More accurate description is, this is a system-level development board based on the ESP32-S3 platform. So the silver module says the S3 N16R8. In common ESP32-S3 module naming, N16R8 refers to a configuration with 16 MB, or I'm really sorry because I forgot what the M means. I just megabyte of PSRAM, and this is this is most likely a third-party S3 N16R8 module, so functionally and electrically close to the ESP32 S3 WROM 1 and 16R8 blah blah, this really long name class of configuration, but exact expressive marketing is not present, so never mind. So back in video, flash is long-term storage. Your firmware, file system, web resources, images, and program code all need to lie here. PSRAM is more like extra workspace during runtime. Display buffers, Arduino buffers, camera frame buffers, network buffers, large arrays, and complex application states may all need that memory. In a simple Arduino project, memory may not be the first thing you think about. But once you start building something closer to a real device, memory becomes one of the most main limits. Web control page 2 needs network stack and the page resources and state buffers. As from SPI display to need graphic data and display buffer, and from camera to needs frame buffers, weak words detection to needs temporary data space and model resources. The meaning of N16R8 system is not just the number are bigger, its main meaning is the project ceiling is higher. This board can support firmware that is much closer to a complete prototype. And the one of the most underrated design choices on this board, the two USB-C ports, and that is the most that is fantastic. Never mind, I just can't find word to express my emotion. So at the surface level, it just looks like two connectors, but from a development perspective, they represent two different paths. The first path, traditional. The computer connects through USB-C to CH343P, USB to UART chip. Then the CH343P communicates with the ESP32-S3 through UART or UART. Yeah, in the future I will call UART. So the CH343P is a translator. This path is major. It is widely supported, useful for flashing firmware, opening for a serial monitor, working with the traditional embedded development workflow. And the second path is native. The ESP32-S3 itself contains a USB serial controller the computer can communicate more directly with the ESP32-S3 through the chip's own native USB capability. This native path can be used for firmware download, CDC serial console, and JTAG debugging. The two passes represent two generations of the development workflow. USB-C to UART emphasizes competitivity, tradition, and stability. Native USB emphasizes the chip's own integrated capability, better debug integration, and more modern USB device development. This also explains why GPIO 19 and GPIO 20 should not be treated casually. They correspond to the native USB-C D- and D+ lines of the ESP32-S3. If you use them as originally GPIO pins and connect other external hardware to them, native USB-C download, CDC, or JTAG may stop working correctly. On the ESP32-S3, a pin is not always just a pin. Some pins are tied to system-level functions inside the chip. So from the previous photo I draw, the board is very likely part of the YD-ESP32-S3 dual USB-C development board family, or a highly similar compatible board. Dual USB-C, RST, and boot buttons, CH343P onboard RGB LED, 22x2-pin header layout, all consistent with YD-ESP32-S3 core board version 1.4, but there is an engineering reason to remain cautious. The RF module in the previous or we showed does not look like a standard expressive WROM 1 module with the usual official laser marketing. Its marketing says S3 N16R8 or Wi-Fi at Bluetooth ISM 2.4G 802.11 BGN, and there appears to be an IPEX or UFL-style RF connector. The official WROM 1 is usually the PCB antenna version. The WROM 1U is usually the external antenna connector version, but this module appears to show both a PCB antenna region and an RF connector. So the careful conclusion is the carrier board strongly resembles the YD-ESP32-S3 family, but the RF module itself is likely a third-party S3 N16R8 module. That means there are things we cannot conclude from the photo alone. Does the RF path use the PCB antenna or the external antenna connectors? If we plug an external antenna, does it actually become active? Does it require changing a 0-ohm resistor or a solder bridge? Do FCC, CE, and SRCC markings correspond to this exact module? So do not treat it looks similar as it identical. Similar appearance does not guarantee identical power design, RF design, solder bridge configuration, and component quality. So the silver module at the top is the concentration point of computation, wireless communication, and memory. It is not just a chip package. It is the brain of the board and also its wireless center. The antenna region is responsible for 2.4 GHz wireless signal transmission and reception. The area around antenna should be kept clear. Metal enclosures large display frames, ground planes, and nearby conductive structures can all affect wireless performance. The RST and boot buttons correspond to reset and boot module control. When automatic download fails, the classic recovery process is hold boot, press reset, then release the boot. So the ESP32-CH343P is the USB to UART chip. It controls the traditional development link. Firmware flashing, serial logs, and debug output often depend on it. The power management section takes the 5 voltage input from USB-C and converts into 3.3 voltage. This leads to a very important point. The ESP32-S3 uses 3.3 logic and it is not 5 voltage tolerant. If we connect 5 voltage UART modules, the 5 volt I23 sensors or the 5V SPI devices, we should use a proper level shifter. And the RGB LED and the PWR-TX RX indicators makes internal system states visible. They are not just decoration. They can show Wi-Fi states, arrow states, operating stage, or simple debug information. And the better way to look at this board, which layer of the system does each component represent, is the power, startup, communication, debugging, wireless, runtime status. So one reason ESP32-S3 is powerful is the GPIO Matrix. Many internal peripheral functions can be routed to different GPIO pins. This gives developers a lot of flexibility, but flexibility also creates traps. Trap 1. GPIO 35, 36, 37 on N16R8 style configurations with OC Octal PSRAM. These pins are usually already used internally by the memory system. Some boards may still print these numbers near the header, but that does not mean they are safe to use as external GPIO pins. The skill screen may tell you that a pin number exists, but the system architecture may tell you that the pin is already occupied. Trap 2. GPIO 20 and 19. They are native USB D- and D+ pins. If you use them for ordinary external hard drive, native USB, CDC, and JTAG function may be affected. Trap 3. ADC2 conflicts with Wi-Fi. If your project needs analog sampling while Wi-Fi is active, you should prefer ADC1 channels whenever possible. Trap 4. Voltage level. The board can be powered through USB, but that does not mean its GPIO pins accept 5 voltage signals. USB provides the power input. The chip logic runs at 3.3 voltage. Those two facts must not be confused. The silk screen tells you a pin number exists. The system architecture tells you whether it's actually available. On the ESP32-S3, a pin may connect it to USB, boot strapling, JTAG, internal memory, ADC touch sensoring, RTC, or wireless related limitations. So, what is this board good at and what is not? It is not. So, it's just suited for general connected controllers, MQTT devices, home assistant nodes, wireless sensor hubs, Bluetooth low energy interaction, phone controlled devices, BLE sensors, BLE gateways. USB related projects have the CDC serial devices, HID experiments, small USB tools, native JTAG debugging. Display and interaction products that include the SPI, display panels, sensor dashboards, desktop status monitor, lightweight AIoT, and voice experiments also support like wake word detection, voice commands, and simple edge processing. But it's not suitable because it is not a 5-volt logic board. It should not directly drive high current loads. It does not have native battery charging management, so it does not include onboard level shifting. Its wireless performance will depend on module quality, antenna environment, power stability, and RF design. And if you wanna connect servos, relays, large displays, or audio amplifiers, or other high current devices, those external loads should usually have their own power source with a shared ground connection to the development board. The best role for this board is not as a power board or a heavy load driver. Its best role is as a control communication and system integration core. So eventually or finally we are step into this. So Arduino teaches us control, and I have to say that, and I'm really thankful for Arduino Uno R3 because this is the capstone for me. Not capstone, but it's just really milestone. Yeah, milestone. I found the word milestone. It's just a milestone for me because I want to share my personal experiment because I was called a child who is totally not understand the thinking of programming. And I really have a dream of programming, but I always just afraid of how to program on a board. But really thankful for this area, whether the OpenAI or cloud, they give us a lot of resource to that a really normal person just can build lots of the programs they want to do. And I have to say that Arduino and a lot of the AI programming is meaning a lot for me. And Arduino teaches control back into video. So Arduino teaches us control, one input, one decision, one output. It gives us the first clear intuition about electronics. ESP32-S3 teaches the system, organization, computation, wireless communication, memory, USB, debugging, peripherals, power and status feedback all need to work together inside one device. So the most interesting part of this ESP32-S3 board is not simplify that it is faster. It is faster. It is not simply that it has more interfaces. The interesting part is that it moves the developer from controlling a circuit to building a connected, embedded system. From this perspective, it is not a simple replacement for Arduino. It is the next layer of abstraction. When your goal is to light something up, Arduino may already be enough. But when your goal is to build a device that can connect, interact, run complex firmware, be debugged, and be expanded, a board like this ESP32-S3 becomes a much more natural platform. On the surface, it is a just development board, but if we look carefully, it is a small embedded system in miniature. I don't know how to read that word. I apologize. Anyway, thank you for watching this video. That's all. Have a good day.